Yes, student, hello everyone. We start our course of lecture formal automata language automated course, and today we have lecture number 15. This lecture will be devoted parsing and ambiguity. So start. We have so far concentrated on the generative aspect of grammars. Given grammar's G capital, we study the set of strings that can be derived using the grammar G capital. In case of practical application, we are also concerned with the analytical side of the grammar. Given as a word W of terminals, we want to know whether or not the word W is in LG. So we may want to find a derivation of the word W. An algorithm that can tell us whether the word W is in LG is a membership algorithm. The term parsing describes finding a sequence of production by which a word W from LG is derived. Parsing and membership. In a word W in LG, we can parse it in the radio fashion. We systematically construct all possible, say, leftmost derivation and see whether any of them match with the word W. Specifically, we start at route 1 by looking at the old production of the form S into X, finding all X that can be derived from S capital into one step. If none of these result in a match with the word W, we go to the next round, in which we apply all applicable production to the leftmost variable of every X. This gives us a set of synthetical forms, some of them possibly leading to the word W. On each subsequent round, we again take all leftmost variables and apply all possible productions. It may be that some of these synthetical forms can be rejected on the grounds that the word W can be never be derived from them. But in general, we shall have on each round a set of possible synthetical forms. After the first round, we have a synthetical form that can be derived by applying a single production. After the second round, we have the synthetical form that can be derived in two steps, and so on. If the word W belongs to LG, then it must be have a leftmost derivation of finite length. Thus, the method will eventually give a leftmost derivation of the word W. Reference below, we shall call these exhaustive message passing or brute force parsing. It is a form of top-down parsing, which we can view after the construction of the derivation tree from the root down. Now, consider the grammar. Following grammar S2 into S capital or as A as capital B or B as capital A or empty word lambda, and the word W, which is equal AABB. Round 1 gives us S onto SS, S onto A, S capital B, S capital onto B, S capital A, and S onto a lambda which is the empty word. The last two of these can be removed from the consideration of the result. Round to them equals synthetical form S onto SS onto SSSS S onto SS onto A S capsule B S capsule S capsule onto S capsule onto B capsule A S capsule and S onto S capsule onto S capsule S capsule onto S capsule, which are obtained by replacing the leftmost S capsule in the synthetical form 1 with all applicable substitutes. Similarly, from the synthetical form 2, we get the additional synthetical forms S into A S capsule B onto A S capsule B, S capsule onto A S capsule B onto A S capsule BB, S onto A S capsule B onto AB S capsule AB, and S onto A S capsule B onto AB. Again, several of these can be removed from concatenation. On the next round, we find the actual target string from the sequence. S onto A S capsule B onto A S capsule BB onto A BB. Therefore, the word AABB is the language generated by the grammar under consideration. The scarcity of siege parsing has serious flaws. The most obvious one is its elementary obviousness. It is not to be used where efficient parsing is required, but even when efficiency of a secondary is there is a more pertinent objection. While the method always parses a word W from the language generated by the grammar G, it is possible that it never terminates for the word not in set of the word generated by grammar G. Yeah, this is essentially the case of the previous example. With the word W which is equal ABB, the method will go to the producing trial synthetical forms and it infinitely unless we built into the some way of stopping. The problem of non-determination of house siege parsing is relative easy to overcome if we restrict the form that the grammar can have. If we examine example 507, we see that the difficulty comes from the production S into empty word lambda. This production can be used to decrease the length of successive synthetical forms, so that we cannot tell easily when to stop. If we do not have any such production, then we have many fewer difficulties. In fact, there are two types of production we want to rule out. Those who form A into empty word lambda as well as those of the form A in capital into B capital. As we will shall see in the next lectures, the restriction does not affect the power of the resulting grammars in any significant way. Example, the grammars of the following form satisfies the given requirement. It generates the language in the example 5.7 without the empty word. Given any word W from alphabet AB, yeah, non with positive length, the exclusive siege parsing method will always terminate in no more than the length of the word W rounds. This is clear because the length of the synthetical form grows by at least one symbol in each round. The length of the word W round, we have either produced a parsing or we know that W does not belong to the language generated by grammars, by the grammar G. The idea in this example can be generated and made into theorem for context-free language in general. Theorem. Suppose that G is context-free grammar that does not have any rules of the form A into lambda or A into B, where A and B belongs to B capital. Then the excavative siege parsing method can be made into an algorithm that for any word our alphabet sigma capital either produces a parsing of the word W or tell us that no parsing is possible. Proof. For each synthetical form, consider both its length and the number of the terminal symbols. Each step in the derivation increases at least one of these. Since neither the length of the synthetical form nor the number of terminal symbols can be exceed the length of the word W. Iteration cannot involve more than 2 multiply to the length of the word W rounds. At each time we either have a successful parsing or the word W cannot be generated by the grammar. It's complete. The proof of this theorem by point 2. While the excavative siege method gives a theoretical guarantee that the person can always be down, its practical usefulness is limited because the number of the synthetical form generated by it may be excessively large. Exactly how many synthetical forms are generated differ from the case to case. More precise general result can be established, but we can put some route upper bound on it. If we restrict our solves to the leftmost derivation, we can have no more than the size of P capital synthetical form after one round, no more than size of P capital in square synthetical form after the second round, and so on. In the proof of theory 5.2, we observe that the parsing cannot involve more than 2 multiplied the letter of the word W round. Therefore, the total number of synthetical form cannot extend and is equal to M and so is such series here, and we get that it's all of P in power 2 multiply the length of the word W plus 1. This indicates that the work of exhaustive siege parsing may grows exponentially with the length of the word, making the cost of the method prohibitive. Of course, the equation, the quality one is not is only be bound, and often the number of synthetical form is much smaller. Nevertheless, practical observations show that the scales siege parsing is very inefficient in the most cases. The construction of more efficient parsing methods for content-free grammars is a complicated matter that belongs to a course of the compiler. We shall not person it here expect for some isolated result. Theorem 5.3. For every context-free grammar, there exists an algorithm that parses any word of the language which is generated grammar. G capital is the number of the step propositional to the length of the word W in the power 3. There are several known methods to achieve this, but all of them are sufficiently complicated that we cannot even describe them without developing some additional result. In next lecture, we shall take this question up again briefly. More detail can be found in the Harrison paper of the year 1978 or in the paper of Hopscroft and Ullman in 1979. One result for not parsing this in detail is that even these algorithms are unsatisfactory. A method in which the work rise with that power of the length of the word, while better than an exponential algorithm, is still quite inefficient. And a parser based on it would need an excessive amount of the time to analyze even a moderately long program. What we would like to have is a parsing method that takes time proportional to the length of the word. We refer to such a method as a linear time parsing algorithm. We do not know any linear time parsing method for context-free language in general, but such algorithm can be found for restricted by important special cases. Definition. Text-free grammar, typically said to be a simple grammar or an S grammar if all its production are of the form A capital into A X, where capital belongs to V, small belongs to G capital, and X belongs to V capital star, and any pair A capital, A small occurs in at most once in the P capital. Example: the following grammar S into A as capital or B as capital or C is a simple grammar. The grammar of the following is not a simple grammar because the pair S A occur in the two production S into AS and S into ASS. Yeah. While the simple grammar are quite restrictive, they are of some interest. As we shall see in the next lecture, many features of common programming languages can be described by simple grammars. If G capital is a simple grammar, then any string or any word in the language generated by grammar G can be parsed with the effort propositional to the length of the word W. To see this, look at the escape siege method at the string W is equal A1, A2, so on, AN. I think there can be at most one rule with S capital on the left, and starting with the symbol A1 on the right. The derivation must be begin with S onto A1, A capital 1, A capital 2, so on A capital M. Next, substitute for the variable A capital 1, but since again there is a most one choice, we must have as drives star onto A1, A2, B capital 1, B2, B capital 2, so on, A capital 2, so on, A capital M. We see from this that each step produces a terminal symbol, and hence the whole process must be completed in no more than the length of the W steps. Ambiguity in grammars and languages. On the basis of our argument, we can claim that every given any word W of the language generated by grammar G capital, as countive each person will be produce a derivation tree for the word W. We say a derivation tree rather than the derivation tree because of the possibilities that a number of different derivation tree may be exist. This situation is referred as to the ambiguity definition. A context-free grammar G capital is said to be ambiguous if there exists some word W in LG that has at least two distinct derivation tree. Alternatively, ambiguity implies the existence of two or more leftmost or rightmost derivation. Example, the grammar in example 5.4 with such production is ambiguous. The sentence AABB has the two derivation tree shown in the following figure. Ambiguity is a common root of the natural languages, where it is tolerated and dealt with a variety of ways. In programming languages, where there should be only one interpretation of each statement, ambiguity must be removed when possible. Often, we can achieve this by writing the grammar in an equivalent unambiguous form. Next example. Consider the grammar G with such with V capital and T capital of the following form and the following production. Then the words of the form such and such are in LG. It's easy to see that these grammar generate a restricted subset of arithmetic expressions for C-like programming languages. The grammar is ambiguous. For instance, the word A plus B star C has two different derivation trees, as shown in the following two figures. First derivation tree and the next derivation tree. One way to resolve the ambiguity is as down the programming manual to associate a precedence rule with the operation plus and star. Since star normally has high precedence that operation plus, we would take the first figure as a correct parsing as indicated that B star C is a sub-expression to be evaluated before performing the addition. However, this resolution is completely outside the grammar. It is better to rewrite the grammar so that only one parsing is possible. Example. To rewrite the grammar in example 5.11, we introduce new variable taking W capital as E capital T capital F capital I capital, and replacing the production with following way. Iteration 3 of the sentence A plus B star C is shown in the following figure. Example, and so it continues. No other derivation tree is possible for this string. The grammar is unambiguous. It is also equivalent to the grammar in example 5.11. It is not too hard to justify these claims in this specific instance, but in general, the question of whether a given context-free grammar is ambiguous or whether two given context-free grammars are equivalent are very difficult to answer. In fact, visual reality shows that there are no general algorithms by which this question can always be resolved. In the foregoing example, the ambiguity can from the grammar in the sense that it could be removed by finding an equivalent unambiguous grammar. In some instances, however, this is not possible because the ambiguity is in the language definition. If L capital is a context-free language for which there exists an unambiguous grammar, then L capital is said to be unambiguous. If every grammar that generates language L is ambiguous, then the language is called inherently ambiguous. It is a somewhat difficult matter even to exhibit to inherently ambiguous language. The best we can to do here is give an example with some reasonably plausible claim that it is inherently ambiguous. Example. So the following language here, language contains the words of such form, is inherently ambiguous context-free language. That language L is context-free is easy to show. We remark that L is consistent of L1, L2, where L1 is generated by the production, yeah, and L2 given in Lewis grammar with the star symbol S2 and production. Then the language L capital is generated by the combination of these two grammar with additional production. S capital into S capital 1 or S capital 2. And the grammar is ambiguous because the string in power n, b in power n, c in power n has two distinct derivations. One starting with S onto S1 and other S onto S2. It does not, of course, follow from this the language L is inherently ambiguous, as there might exist some other unambiguous grammar for it. But in the same way, L1 and L2 have conflicting requirements. The first, we're putting a restriction on the number of symbol A and symbol B. While the second does not same for the symbol B and the symbols C. A few tries will quickly convince you of the possibility of combining these requirements in the single set of the rules that cover the case M is equal M uniquely. Rigorous arguments thought quite technical, and one proof can be found in the Harrison paper, which was published in 1878. So I finish my lecture. Thank you for your attention. Uh, I wish you good luck, good health, and finish Russian accuracy wrong.